Hi everyone. In this video, we are going to briefly cover the remainder of section 7.5, dealing with conic sections. We're just going to look at the last part, which is on hyperbolas. We start with a definition for hyperbolas. A hyperbola is a set of all points where the difference between their distances from two fixed points, called the foci, is constant. So with ellipses, it was that the sum of the distances from the two fixed points is constant. The difference here is with hyperbolas, it's the difference. Really, the definition isn't like absolutely crucial for you to know to be successful in this section. What they look like. So here is my hyperbolas, two different branches, if you will. We have lots of terms here. We have the center. This is called a vertex. These 2 points right here. The foci are outside. They're on the outside of the hyperbola. Our distance A is the distance out to the vertices. Our distance B doesn't really have significance on the actual graph, other than excuse me, other than the fact that that distance B and A, that actually determines the slope of the asymptotes, which is kind of cool. B over A is the slope of these two asymptotes, and then negative in the case of this direction when the vertices are in the x direction. That way, we can also have hyperbolas like this, and the slope would just be the opposite. It'd be A over B. Let me slide down here to the equation of a hyperbola in standard form. Okay, the difference with hyperbolas from ellipses is here, right in the center, is that subtraction. If that were a plus sign, this would be the graph of an ellipse. When it is a subtraction sign, it is the graph of a hyperbola. Tons of additional information on here. The key stuff being this Pythagorean relationship if we're asked to find anything involving the foci. And then that h comma k, that is our center of our hyperbola. And then down here at the bottom, if the major axis is vertical, that just switches the a and b. Notice the a is underneath the x when the major axis is horizontal. The a is underneath the y when the major axis is vertical. So now let's look at an example. We're given an equation, which it may not be immediately obvious, or maybe it is, that it's the equation of a hyperbola. And we need to put it in standard form, graph the resulting hyperbola, and then come up with the equations of the asymptotes. And so my x squared, my y squared, they're both squared, so that tells me hyperbola or ellipse. And the fact that it's the x squared minus the y squared means that it is definitely a hyperbola. So let's group our x's together when we write this down. We have 9x squared plus 36x, group my y's together, minus 16y squared plus 32y, and I'm going to add that 124 to the other side. All right, now the next step is to factor the 9 out. 9 times x squared plus 4x, and I'm going to write plus blank inside of that parentheses. And then we'll factor the 16 out of the y squared and y terms, but I'm also going to take that negative out in front. So minus 16 times y squared, that 32y becomes just minus 2y plus blank equals 124. Now we complete the square, half of the b, the coefficient of x, and then square it. Half of 4 squared is 2, squared is back to 4, and then half of the negative 2 is negative 1, squared is 1. Okay, then it is important to consider what did I actually add on the left-hand side. To the first parentheses, I added 9 times 4 is 36. To the second parentheses, I didn't add anything to the second parentheses. That's a 1 inside with a negative 16 in front. So I actually subtracted 16 in the y parentheses. Now we can complete our square. Our squares, 9 times x plus 2, that quantity squared, minus 16 times y minus 1, that quantity squared, equals 124 plus 36 minus 16. Sounds like it should be 144. Our next step, we're going to divide both sides of the equation by 9 times 16, which happens to be 144. divide everything by 144. We're left with the x plus 2 quantity squared over 16 minus the y minus 1 quantity squared over 9 equals 1. Okay, so now what important pieces do we need out of that equation if we're going to draw the graph of this hyperbola? Well, our center, that is at -2 comma 1. That's really important. The value of a is 4. The value of b is 3. And the fact that the 16 is larger, the A is 4, B is 3, that tells me that if I draw a really, really poor sketch, that tells me that my hyperbola looks like that. If the number underneath the y term were larger, it would be oriented, the hyperbola would be oriented vertically. Okay, so now how do we actually go from this to creating our graph? Let me add on a little grid here. Okay, and poof, there's my grid. Let's see. So we're going to start at our center. Let me do this graph in red. Our center is at -2 comma 1. So right there is my center, but that's not actually a point on my hyperbola. All right, that helps me to first find my vertices. The fact that A is 4 means I'm going to go 4 units in the x direction. 1, 2, 3, 4. That's one of the vertices. 1, 2, 3, 4. That's another one of the vertices over there at negative, I think that's -6. Okay, so that gives me 2 points on my hyperbola. And then in my opinion, the best way to kind of draw these, the branches of the hyperbola is to use this A and B to get the rise over run for the asymptotes. Okay, and so the way I like to do that, B is 3, A is 4, so I'm going to go up 3 over 4. So 1, 2, 3, and then 1, 2, 3, 4, like that. And that gives me a little slanted line there. And then down 3 and back 4. 1, 2, 3, and back 4 is going to be right there. Draw a little curve or a little line like that, dotted line. And then the same thing in the other direction is going to give me a point right there. And I can draw a nice little slanted line. And then a point down here. Like that, okay? Those are the asymptotes, and that, when I draw the branches for my hyperbola, those are the lines that the hyperbola gets closer and closer to, but never touches and never crosses. Like that. And like that. So we technically draw these hyperbolas really with only 1 or 2 good points, but the asymptotes are what helps us to determine their shape, how curvy they are, I guess, if you will. And then just to clarify, in case there's questions about how I knew to go up 3 and over 4, right? This 4 is in the x direction. That's underneath the x part of the equation. This is a y direction, so this is a rise, this is a run. Okay, and what it kind of does here, you can look at it this way also, is it like puts a little those 2 or those 4 points make like a little box here, like so. Okay, and it's up 3 and over 4, down 3 and back 4 to get to each. Whoops, to get to each of these 4 points. So I can graph those asymptotes without finding their equation. The problem does ask me to actually get the equation of the 2 asymptotes. And the way that you do that is using the point slope formula. Y minus y1 equals m times x minus x1. I've already talked about how the slope of that asymptote is 3/4. It's actually, to be specific, positive or negative 3/4. So we can write plus or minus. And then x minus the center is the other point, is the 1 point on the asymptote. So it's -2, so that becomes x plus 2, and y minus 1. So we could write them separately. The way that OpenStax leaves the answer is as y equals 1 plus or minus 3/4 times x plus 2. And if I wanted to get the actual equation, to write them separately and simplify, I could do that, but I'm going to leave the answer like that. All right, so we have the equations of the asymptotes, we have our graph, And then where is the equation? Here is the equation of the hyperbola. Now, one thing that OpenStax does not do that I think it should is doing calculus with all of these conic sections. I'm not sure why it doesn't. When I taught the course previously, we introduced and talked about the conic sections and then did some calculus with them. I will throw this in as an example, but I don't think that any actual derivatives or integrals come up on the homework set. Okay, so in this example, we're going to find an equation of a line tangent of the line tangent to the curve at the given point. The curve is y squared equals 8x, and the given point is 8, negative 8. Okay, if we want a tangent line, we know we need the derivative. If I'm taking the derivative of this conic section, which happens to be a parabola, I need to take the derivative implicitly. So whether it's a parabola, hyperbola, or an ellipse, we need that other tool for differentiation. In this case, it's implicit differentiation. So when I take the derivative of y squared, the answer is 2y, but also times dy over dx. And the derivative of 8x is just 8. So the derivative, not too challenging, but you do have to remember that it's using implicit differentiation. So then my derivative dy over dx is 8 divided by 2y, or I can write that as 4 over y. So that tells me that allows me to find the slope of my tangent line. M is equal to 4 divided by the y coordinate is negative 8, or negative a half. There's my slope. And then we go y minus y1, m times x minus x1, y minus my y coordinate is negative 8 again, equals negative a half times x minus regular 8, y plus 8, negative a half x, and then it's going to be plus 4. Negative half times negative 8 is positive 4. And then y equals negative 1/2, subtract the 8, negative 1/2 x minus 4 is the equation of my tangent line. So nothing too crazy with this example. This is the final example of the course other than the review problems that we go through. And that takes us to the end of the section. Thank you very much for listening. Please let me know if you have questions. Come with some questions to class tomorrow, and have a fantastic day.